Hey there, fellow stargazers. How has your evening been treating you? I hope you found a comfortable spot to settle in, because tonight we're embarking on a journey that will stretch your imagination to its absolute limits. We're going to explore something so vast, so incomprehensibly enormous, that it challenges everything we think we know about the scale of existence itself. What if I told you that somewhere out there in the cosmic darkness, there are stars so massive that if you placed one at the center of our solar system, it would swallow not just Earth, not just Mars, but extend all the way out past Jupiter's orbit. Stars so large that our own sun, that brilliant ball of fire that gives us life, would appear as nothing more than a grain of sand next to a basketball. Tonight, we're diving deep into the realm of the universe's most colossal giants. The top 5 biggest stars that human eyes have ever detected. These aren't just large objects floating in space. They're cosmic monsters that rewrite the rules of physics, challenge our understanding of stellar evolution, and force us to confront the mind-bending reality of just how small we truly are in this vast cosmic theatre. The visuals are here to guide you through this stellar odyssey, but feel free to close your eyes, let your imagination drift, and allow these cosmic giants to paint themselves across the canvas of your mind. And I'd love to know where you're watching from tonight. Drop your location in the comments below. Are you gazing up at actual stars through your window right now? There's something beautifully poetic about learning about the universe's largest stars, while perhaps catching a glimpse of distant suns in your own night sky. If you find wonder in these explorations of cosmic extremes, I'd be deeply grateful if you'd consider subscribing and giving this video a like. It helps the algorithm connect with more curious minds like yours, souls who look up at the night sky and dare to ask just how big things can really get out there. Let's dive right in. Now, before we meet these stellar behemoths, we need to understand something fundamental about the challenge of measuring the universe's largest stars. You see, determining which star holds the title of biggest isn't as straightforward as you might think. It's not like measuring buildings or mountains here on Earth where we can use precise instruments and get exact numbers. When we're dealing with stars thousands of light years away, the very act of measurement becomes an exercise in pushing the boundaries of human ingenuity. These stellar giants don't have sharp, defined edges like a basketball or a marble. Instead, they have what astronomers call diffuse photospheres, layers of glowing gas that gradually fade into the vacuum of space. Where exactly does the star end and empty space begin? It's like trying to measure the size of a cloud, except the cloud is a ball of nuclear fire burning at temperatures that would vaporize any known material instantly. The methods astronomers use to determine stellar sizes are ingenious but fraught with uncertainty. They rely on complex calculations involving the star's luminosity, how bright it appears to us, its surface temperature, and its distance from Earth. But here's where it gets tricky. If you're off by even a small amount in measuring the distance to a star, your calculation of its size can be dramatically wrong. It's like trying to judge the size of a campfire from miles away in the fog. You might think you're looking at a bonfire when it's actually a forest fire, or vice versa. This uncertainty has led to some dramatic revisions in our cosmic record books. Stars that once held the title of largest in the universe have been dethroned not because we found bigger ones, but because we realized our measurements were wrong. It's a humbling reminder that even our most advanced science is constantly evolving, constantly correcting itself as we develop better tools and more sophisticated understanding. What makes this even more challenging is that these massive stars aren't static objects. They pulse and vary in size over time, sometimes dramatically. Their outer layers expand and contract like a slow cosmic heartbeat, driven by the violent nuclear processes occurring in their cores. Some of these giants can change their radius by hundreds of millions of kilometers over periods of months or years. Imagine trying to measure something that's constantly changing size on a scale so vast that light itself takes hours to travel from one side to the other. The stars we're about to explore exist in a realm where the normal rules of stellar physics are pushed to their absolute limits. These are objects so large that they shouldn't exist according to some theoretical models. They challenge our understanding of how matter can hold itself together under its own gravity, how nuclear fusion can continue to power such enormous structures, and how the delicate balance between a star's outward radiation pressure and inward gravitational pull can be maintained. But perhaps what's most remarkable about these cosmic giants is that they represent the final spectacular chapter in the life stories of the most massive stars in our universe. They're not just large, they're dying. These red supergiants and hypergiants are stars that have exhausted the hydrogen fuel in their cores and are now burning heavier elements in a desperate attempt to stave off their inevitable gravitational collapse. Their enormous size is actually a symptom of their impending doom. Their outer layers puffed up to incredible dimensions as their cores contract and heat up. In their death throes, these stars become some of the most luminous objects in the universe, shining with the light of hundreds of thousands of suns. Yet despite their incredible brightness, their surfaces are actually cooler than our own sun. This seeming contradiction, this interplay between size, temperature, and luminosity, reveals the elegant complexity of stellar physics and the beautiful mathematics that govern how stars live and die. As we prepare to meet these 5 cosmic giants, remember that you're about to encounter objects that exist on scales that dwarf human experience. We're talking about stars with radii measured in billions of kilometers, objects so large that if you could somehow travel at the speed of light, it would take hours just to journey from their center to their surface. If our sun were the size of a marble, some of these stars would be larger than a 2-story house. These aren't just abstract numbers or scientific curiosities. These stars are fundamental to the story of our universe. They're the cosmic forges where the heaviest elements are created, the stellar furnaces that will one day enrich the cosmos with the building blocks needed for planets, for chemistry, for life itself. When these giants finally collapse and explode as supernovae, they'll scatter their enriched material across vast regions of space, seeding future generations of stars and planetary systems. The first star on our journey takes us to a realm where theoretical physics meets observational astronomy in a cosmic dance of uncertainty and wonder. This is Stevenson 2-18, a star so large that its very existence challenges what we thought we knew about the limits of stellar size. Located roughly 19,000 light-years away in the constellation Scuti, this red hypergiant represents either the most extreme example of stellar evolution we've ever discovered, or possibly a measurement so extraordinary that it pushes the boundaries of what's physically possible. When astronomers first calculated the size of Stevenson 2-18, the numbers were so staggering that they had to check and recheck their work. According to their measurements, this star has a radius approximately 2,150 times larger than our Sun. To put this in perspective that the human mind can begin to grasp, if Stevenson 2-18 were placed at the center of our solar system, its surface would extend far beyond the orbit of Saturn. We're talking about a star so enormous that Saturn, that magnificent ringed giant that takes light over an hour to reach from the sun, would be buried deep inside this stellar monster. The sheer volume of Stevenson 2-18 is perhaps even more mind-bending than its radius. This single star contains roughly 10 billion times the volume of our Sun. Imagine trying to fill this cosmic giant with sun-sized stars. You would need 10 billion of them. That's more stars than exist in some entire galaxies. It's a scale that reduces our own solar system to something smaller than a speck of dust in comparison. But here's where the story of Stevenson 2-18 becomes as much about the limits of human knowledge as it is about the limits of stellar physics. The measurements that give us this star's incredible size come with enormous uncertainties. The distance to this star, a crucial component in calculating its size, carries an error margin of more than 50%. That means our estimate of its size could be off by hundreds of solar radii in either direction. This uncertainty isn't just a technical problem, it's a fundamental challenge that reveals how we're pushing against the very boundaries of what we can know about the universe. Stevenson 2-18 is so far away and so embedded in cosmic dust and gas that obtaining precise measurements becomes an exercise in extracting whispers of information from the cosmic noise. Every photon of light that reaches us from this distant giant has traveled for nearly 20,000 years, carrying with it a message encoded in wavelengths and intensities that we must decode with mathematical precision. What makes Stevenson 2-18 even more intriguing is that according to our current theories of stellar evolution, it shouldn't exist. Theoretical models suggest that stars can't grow larger than about 1,500 times the size of our Sun before they become gravitationally unstable. Beyond this limit, a star should either collapse under its own weight or blow away its outer layers in violent stellar winds. Yet here we have Stevenson 2-18, seemingly defying these theoretical constraints by a significant margin. This discrepancy between theory and observation opens up fascinating questions about our understanding of stellar physics. Are our models incomplete? Are there physical processes occurring in the most extreme stars that we haven't yet discovered? Or is Stevenson 2-18 simply a measurement error, a cosmic mirage created by the challenges of observing objects at such vast distances? The effective temperature of Stevenson 2-18 adds another layer to this cosmic puzzle. At approximately 3,200 degrees Kelvin, it's actually cooler than our Sun's surface temperature of about 5,800 degrees Kelvin. This might seem counterintuitive. How can such a massive star be cooler than our relatively small Sun? The answer lies in the star's evolutionary state and the physics of stellar atmospheres. Stevenson 2-18 is what astronomers classify as a red hypergiant, a type of star that represents one of the final evolutionary stages for the most massive stars in the universe. These stars have exhausted the hydrogen fuel in their cores and are now burning helium and heavier elements in a series of nuclear reactions that occur in shells around their contracting cores. This process causes the star's outer layers to expand dramatically, while simultaneously cooling down. Think of it like a balloon being inflated. As the balloon gets larger, the same amount of material is spread over a much larger surface area, making each part of the surface less dense and, in the case of a star, cooler. The total energy output of Stevenson 2-18 is enormous, roughly 440,000 times more luminous than our Sun. But this energy is spread across such a vast surface area that the temperature at any given point is relatively low. This cooling effect is what gives red hypergiants their characteristic color. Despite being among the most luminous objects in the galaxy, they glow with a deep red light that speaks to their relatively low surface temperatures. It's a beautiful example of how the universe can create objects that are simultaneously among the brightest and coolest stars we know. The location of Stevenson 2-18 within our galaxy also tells us something important about these stellar giants. It lies in the direction of the constellation Scuti, toward the center of our Milky Way galaxy, in a region rich with massive stars and stellar clusters. This isn't coincidental. The most massive stars, the ones that can evolve into red hypergiants like Stevenson 2-18, are relatively rare and tend to form in regions where there's an abundance of the raw materials needed for star formation. These massive stars also have relatively short lifespans compared to smaller stars like our Sun. While our Sun will shine for approximately 10 billion years, a star massive enough to become a red hypergiant might live for only 10 to 20 million years. They burn through their nuclear fuel at such a prodigious rate that their entire existence, from birth to explosive death as a supernova, occurs in what is essentially a cosmic blink of an eye. This short lifespan means that red hypergiants like Stevenson 2-18 are rare and precious objects in the cosmic catalogue. They represent fleeting moments in the universe's long history, brief periods when matter organizes itself into structures of almost incomprehensible scale and luminosity. Observing them is like catching a glimpse of cosmic fireworks just before they explode in spectacular fashion. The study of Stevenson 2-18 also highlights the collaborative nature of modern astronomy. The measurements that reveal this star's enormous size were made using radio telescopes, specifically the Australia Telescope Compact Array. By observing the star at radio wavelengths, astronomers can peer through much of the cosmic dust that obscures our view at visible wavelengths, allowing them to make more accurate measurements of the star's properties. This multi-wavelength approach to astronomy, using different types of light from radio waves to X-rays, has revolutionized our understanding of the universe's most extreme objects. Each wavelength of light tells us something different about a star's properties, and by combining observations across the electromagnetic spectrum, we can build up a more complete picture of these cosmic giants. As we contemplate Stevenson 2-18, we're forced to confront the incredible diversity and extremes that exist in our universe. Here is an object so large that it challenges our theoretical understanding, so luminous that it outshines hundreds of thousands of suns, yet so cool that its surface temperature is lower than that of our own modest star. It's a reminder that the universe delights in creating objects that push against the boundaries of what seems possible, forcing us to expand our understanding of the cosmic order. Whether Stevenson 2-18 truly deserves the title of largest known star remains an open question, one that future observations and improved measurement techniques will help resolve. But regardless of where it ultimately ranks in the cosmic size hierarchy, it serves as a magnificent example of the universe's capacity for creating objects of stunning scale and beauty, stellar giants that remind us of our small but significant place in the grand cosmic story. The second giant on our cosmic journey takes us to a different corner of our galaxy, to a star that exists within one of the most remarkable stellar neighborhoods ever discovered. This is W26, officially known as Westerlund 1W26, a red supergiant that dwells on the outskirts of the Westerlund 1 superstar cluster, approximately 11,500 light-years from Earth in the constellation Ara. What makes W26 particularly fascinating isn't just its enormous size, though that alone would be enough to capture our imagination. With a radius calculated to be approximately 1,540 times that of our Sun, W26 would engulf the orbit of Jupiter if placed at the center of our solar system. But what truly sets this stellar giant apart is the extraordinary luminosity it displays, shining with the combined light of roughly 380,000 suns. making it one of the most luminous red supergiants we've ever discovered. Imagine standing on a hypothetical planet orbiting a normal star like our Sun, then suddenly replacing that star with W26. The sky wouldn't just become brighter, it would transform into something almost beyond comprehension. The amount of energy pouring down would be so intense that any atmosphere would be stripped away instantly, and the surface of any rocky planet would be vaporized within moments. This is the raw power contained within these stellar behemoths, energy outputs that dwarf anything in our earthly experience. The Westerlund 1 cluster, where WW6 resides, is itself a cosmic wonder, a stellar nursery that has given birth to some of the most massive and luminous stars in our galaxy. Discovered in 1961 by Swedish astronomer Bengt Westerlund during an infrared survey of the southern sky, this cluster was initially hidden from view by enormous clouds of cosmic dust. It's located in what astronomers call the zone of avoidance, a region of the sky where dust in the plane of our galaxy blocks much of the visible light from more distant objects. This dusty veil that initially concealed Westerlund 1 from astronomers also tells us something important about the nature of massive star formation. These cosmic giants don't form in the pristine vacuum of empty space. Instead, they're born in regions rich with gas and dust, the raw materials needed to build stars of such incredible mass. The very dust that hides them from our view is both a byproduct of previous generations of massive stars and the building material for future ones. The environment within the Westerlund 1 cluster is unlike anything we experience in our relatively quiet corner of the galaxy. Here, massive stars crowd together in cosmic proximity, their intense stellar winds and radiation creating a turbulent, high-energy environment. The cluster contains numerous red supergiants, blue hypergiants, and other exotic stellar types, all of them representing different evolutionary stages of the most massive stars in the universe. W226's position on the outskirts of this stellar metropolis is significant. While it's part of the cluster, it's not buried deep within the chaotic core where stellar interactions are most intense. This peripheral location may have allowed it to maintain its enormous size without being disrupted by the gravitational influences or stellar winds of nearby massive neighbors. It's like a cosmic suburb where a giant star can exist in relative peace while still being part of a larger stellar community. One of the most remarkable discoveries about W26 came in 2013, when astronomers using the European Southern Observatory's Very Large Survey Telescope made an observation that fundamentally changed our understanding of red supergiant stars. They discovered that W26 is surrounded by a glowing cloud of ionized hydrogen, a nebula that extends more than a parsec from the star itself. That's roughly 3¼ light years, a distance so vast that light from the star takes over 3 years to reach the outer edges of this glowing envelope. This discovery was groundbreaking because it represented the first time an ionized nebula had been detected around a red supergiant through optical emission lines. Until this observation, astronomers didn't expect red supergiants to be capable of ionizing the gas around them to such an extent. Red supergiants are cooler stars, and their radiation shouldn't be energetic enough to strip electrons from hydrogen atoms over such vast distances. The existence of this ionized nebula around W26 suggests that our understanding of red supergiant physics is still incomplete. Perhaps these stars undergo periods of enhanced activity where they produce more energetic radiation than we previously thought possible. Or maybe the interaction between the star's intense stellar wind and the surrounding interstellar medium creates conditions that we haven't fully modeled in our theoretical frameworks. The stellar wind from W26 is itself a phenomenon of staggering proportions. Red supergiants like W26 are known for their powerful stellar winds, streams of charged particles flowing away from the star at hundreds of kilometers per second. These winds carry away significant amounts of the star's mass over time, gradually reducing the star's total mass while enriching the surrounding space with heavy elements forged in the star's nuclear furnace. The mass loss rate from W26 is estimated to be extraordinarily high, even by red supergiant standards. The star is literally blowing itself apart, losing mass equivalent to our entire sun every few 100,000 years. This might sound like a long time, but in astronomical terms, it's incredibly rapid. Over the course of the star's lifetime, it will shed a significant fraction of its original mass into the surrounding space. This mass loss process is driven by the star's enormous luminosity and the radiation pressure it creates. Photons streaming outward from the star's surface carry momentum, and when they interact with particles in the star's atmosphere, they can actually push that material away from the star. For the most luminous stars like W26, this radiation pressure can overcome the star's gravitational pull, driving powerful stellar winds that strip away the outer layers. The temperature of W26's surface, approximately 3,450 degrees Kelvin, places it firmly in the category of cool stars, despite its enormous energy output. This relatively low temperature is what gives the star its characteristic red color and explains how it can be so luminous while still being classified as a cool star. The star's surface area is so vast that even at this relatively low temperature, the total energy output is astronomical. To understand the relationship between W26's size, temperature, and luminosity, imagine trying to heat a room with candles. A single candle produces a certain amount of heat and light. If you want to heat a much larger room to the same temperature, you could either use much hotter candles or use many more candles at the same temperature. W26 is like having an enormous number of candles, each one relatively cool, but together producing an incredible amount of heat and light. The spectral classification of W26 as an M-type supergiant tells us about the specific characteristics of its light output. M-type stars are the coolest main sequence stars, characterized by their red color and the presence of molecular features in their spectra. When a star reaches supergiant status while maintaining this cool temperature, it indicates that the star has evolved significantly from its main sequence origins. The evolutionary path that led to W26's current state began with a star that was likely 25 to 40 times more massive than our Sun when it first formed. Such massive stars have relatively short lifespans, burning through their nuclear fuel at prodigious rates. The star spent most of its life as a hot, blue main sequence star, fusing hydrogen into helium in its core at temperatures and pressures that dwarf anything achievable on Earth. As the hydrogen fuel in the core became depleted, the star began the complex evolutionary process that ultimately led to its current red supergiant phase. The core contracted and heated up, while the outer layers expanded dramatically. This expansion caused the surface temperature to drop even as the star's total luminosity increased, creating the cool but incredibly bright object we observe today. The future of W26 is written in the physics of stellar evolution. Stars this massive and luminous cannot maintain their current state indefinitely. The nuclear processes occurring in its core are becoming increasingly unstable, burning heavier and heavier elements in a desperate attempt to maintain the energy output needed to support the star's enormous structure. Eventually, the star will reach a point where no further nuclear fusion can occur, and the core will collapse catastrophically. When that moment arrives, W26 will likely explode as a supernova, one of the most energetic events in the universe. The explosion will be visible from thousands of light years away, and will briefly outshine the entire Westerlund 1 cluster. The heavy elements created in the star's core and during the explosion itself will be scattered across vast regions of space, enriching the interstellar medium with the building blocks needed for future generations of stars and planets. The study of W26 and other members of the Westerlund 1 cluster provides astronomers with a unique laboratory for understanding massive star evolution. Because all the stars in the cluster formed at roughly the same time and from the same initial material, they represent different evolutionary paths for stars of different initial masses. By studying the entire population, astronomers can piece together the complete story of how the most massive stars live and die. The observations of W26 also highlight the incredible advances in astronomical instrumentation that have occurred over the past few decades. The discovery of the ionized nebula around the star required extremely sensitive detectors capable of measuring faint emission lines against the bright background of the star itself. The precise measurements of the star's size and luminosity depend on sophisticated models that account for the effects of interstellar dust, stellar variability, and the complex physics of stellar atmospheres. As we contemplate W26 in all its magnificent enormity, we're reminded that the universe contains objects that exist on scales almost beyond human comprehension. This single star, shining with the light of nearly 400,000 suns, represents just one member of a cluster containing dozens of similarly extreme objects. The Westerlund 1 cluster as a whole contains more total luminosity than millions of stars like our Sun, all concentrated in a region of space just a few dozen light-years across. The existence of stars like W26 also speaks to the incredible efficiency of the universe in creating complex, massive structures from the simple ingredients of hydrogen and helium. Through the inexorable pull of gravity and the transformative power of nuclear fusion, the cosmos has managed to create objects of stunning beauty and complexity, stellar giants that serve as beacons of light across vast distances of space and time. Our third stellar giant carries us beyond the boundaries of our own galaxy to a neighboring cosmic island floating in the vast darkness of intergalactic space. This is WOH G64, a yellow hypergiant that holds the remarkable distinction of being the first star outside the Milky Way to be directly imaged by human technology. Located 160,000 light-years away in the constellation Dorado, this massive star resides not in our galaxy, but in one of its satellite companions, the Large Magellanic Cloud. The journey of light from WOH G64 to our telescopes represents a voyage across one of the largest scales we can meaningfully observe in our local cosmic neighborhood. When the photons now reaching our detectors first began their journey, they left the surface of a star in another galaxy entirely. They traveled across the void between galaxies, through regions of space so empty that matter exists at densities lower than the best vacuum we can create in our laboratories on Earth. What makes WOH G64 particularly fascinating is how it challenges our assumptions about stellar behavior and variability. This star has been under astronomical observation for decades, and during that time, it has displayed behavior that has fundamentally altered our understanding of how the largest stars evolve and change. Recent observations have revealed something almost unprecedented in stellar astronomy. WOH G64 has actually shrunk significantly over the past decade. Imagine watching a mountain slowly deflate before your eyes, and you begin to approach the scale of change we're discussing. In 2014, WOH G64 was measured to have a radius of approximately 1,540 times that of our Sun. By 2024, that measurement had dropped to roughly 800 solar radii. The star had literally halved in size over the course of a single decade. a transformation so rapid that it challenges everything we thought we knew about the timescales of stellar evolution. This dramatic shrinkage represents more than just a change in size. It signals a fundamental transformation in the star's internal structure and evolutionary state. WOH G64 has transitioned from being a red supergiant to what astronomers now classify as a yellow hypergiant, a change that reflects alterations in the star's surface temperature and the nuclear processes occurring in its core. It's as if we're watching stellar evolution in fast forward, witnessing changes that normally occur over hundreds of thousands of years, compressed into a mere decade. The physics behind this rapid transformation involves processes that operate on scales and in conditions that push the boundaries of our theoretical understanding. The star's core is undergoing violent changes as different nuclear burning phases ignite and extinguish in complex cycles. These changes in the core's energy output drive corresponding changes in the star's outer layers, causing them to expand and contract like a cosmic balloon being inflated and deflated by forces beyond human experience. The temperature of WOH G64's surface during its red supergiant phase was approximately 3,200 degrees Kelvin, giving it that characteristic cool red glow despite its enormous luminosity. As it has evolved into its current yellow hypergiant state, the surface temperature has increased, shifting the star's color from deep red toward yellow. This temperature increase, combined with the star's reduced size, has altered the entire character of the star's radiation output. The luminosity of WOH G64 remains staggering even after its recent changes. Current estimates place its brightness at roughly 282,000 times that of our Sun, making it easily visible across the 160,000 light-year gulf that separates us from the Large Magellanic Cloud. To put this in perspective, if WOH G64 were placed at the same distance from Earth as our nearest stellar neighbor, Proxima Centauri, it would appear brighter in our sky than the full moon. The energy output from this single star exceeds that of hundreds of thousands of normal stars combined. The mass loss characteristics of WOH G64 represent another extreme in stellar physics. During its most active periods, this star has been observed to lose mass at rates that are extraordinary, even by the standards of red supergiants. The stellar wind from WOH G64 carries away material equivalent to several Earth masses every single year, a rate of mass loss so extreme that it would strip away our entire planet's worth of material in the time it takes you to read this sentence. This intense mass loss creates a complex environment around the star, filled with shells and streams of ejected material that interact with the surrounding interstellar medium in fascinating ways. The material being expelled carries with it the heavy elements created in the star's nuclear furnace, carbon, oxygen, silicon, and iron, that will eventually become incorporated into future generations of stars and planets. WOH G64 is literally seeding its corner of the Large Magellanic Cloud with the building blocks of rocky worlds. Recent discoveries have revealed that WOH G64 is not a solitary giant, but part of a binary system, paired with a smaller companion star. This companion, classified as a B-type star, orbits the hypergiant in a complex gravitational dance that may be influencing the primary star's evolution and mass loss behavior. The interaction between these two stars creates what astronomers call a symbiotic system, where material flowing from the larger star can be captured by the smaller companion, creating unusual spectral signatures and potentially affecting both stars' evolutionary paths. The discovery of this binary nature adds another layer of complexity to understanding WOH G64's behavior. The gravitational influence of the companion star may be responsible for some of the unusual mass loss patterns observed, creating asymmetries in the stellar wind that lead to the formation of complex structures in the surrounding nebula. It's possible that the recent dramatic changes in the primary star's size and temperature are related to this binary interaction, though the exact mechanisms remain poorly understood. The location of WOH G64 within the Large Magellanic Cloud provides astronomers with a unique opportunity to study massive star evolution in an environment different from our own galaxy. The Large Magellanic Cloud has a lower metallicity than the Milky Way, meaning it contains fewer heavy elements relative to hydrogen and helium. This difference in chemical composition can significantly affect how stars form and evolve, potentially explaining some of the unusual characteristics observed in WOH G64. The stellar winds from WOH G64 have created a remarkable torus-shaped structure around the star, a donut of material that extends for vast distances into space. This torus represents the accumulated mass loss from the star over thousands of years, material that has been shaped and sculpted by the complex interplay of stellar radiation, magnetic fields, and the gravitational influences of the binary companion. The study of this torus provides insights into the star's mass loss history and helps astronomers understand the processes that govern the evolution of the most massive stars. The variability of WOH G64 has changed dramatically along with its physical transformation. During its red supergiant phase, the star displayed what astronomers call semi-regular variability, with predictable cycles of brightness changes that occurred over periods of several hundred days. As it has evolved into a yellow hypergiant, this variability has become irregular and unpredictable, suggesting that the internal processes driving the star's energy output have become chaotic and unstable. This transition from regular to irregular variability is more than just an observational curiosity. It provides crucial insights into the internal structure and dynamics of the star. Regular pulsations typically indicate that a star's internal structure is relatively stable, with well-defined layers and predictable energy transport mechanisms. Irregular variability, on the other hand, suggests that the star's interior has become turbulent and unstable, with competing physical processes creating a chaotic environment that defies simple periodic behavior. The future evolution of WOH G64 remains highly uncertain, partly because yellow hypergiants represent such a rare and poorly understood phase of stellar evolution. These stars exist in a transitional state between red supergiants and their final evolutionary endpoints, whether that be a return to a blue supergiant phase or a direct progression toward core collapse and supernova explosion. The rapid changes observed in WOH G64 suggest that this transitional phase may be much shorter and more dynamic than previously thought. The study of WOH G64 has been greatly enhanced by advances in interferometric techniques that allow astronomers to resolve the star's disk and surrounding environment with unprecedented detail. These observations have revealed not just the star's changing size, but also the complex structures in its immediate vicinity, including asymmetric brightness patterns on the star's surface and detailed mapping of the surrounding dusty torus. Such observations would have been impossible just a few decades ago and represent the cutting edge of current astronomical capability. The implications of WOH G64's rapid evolution extend beyond the study of individual stars to our broader understanding of galaxy evolution and chemical enrichment. Massive stars like WOH G64 play crucial roles in enriching their host galaxies with heavy elements, and the rate at which they evolve and eventually explode as supernovae affects the overall chemical evolution of galactic systems. The discovery that such stars can undergo rapid changes in their evolutionary timescales may require revisions to models of galactic chemical evolution. As we observe WOH G64 continuing its dramatic transformation, we're witnessing one of the universe's most spectacular ongoing experiments in stellar physics. This star is providing us with a real-time laboratory for studying processes that normally occur over timescales far longer than human civilization has existed. Every observation adds new pieces to the puzzle of how the most massive stars live out their final chapters before their inevitable, explosive deaths. The story of WOH G64 reminds us that the universe is not a static place, but a dynamic, ever-changing cosmic theatre, where even the largest and most stable-seeming objects can undergo dramatic transformations. This yellow hypergiant, shrinking and brightening in its distant galaxy, serves as a reminder that stellar evolution is an ongoing process, and that some of the most interesting chapters in a star's life may occur in its final moments before catastrophic collapse. Moving deeper into our cosmic catalogue, we encounter our fourth stellar giant, a star that for many years held the undisputed title of largest known star in the universe. This is Scuti, a red supergiant located approximately 9,500 light-years from Earth in the constellation Scutum, nestled in the rich star fields near the center of our Milky Way galaxy. The story of Scuti is not just one of incredible size, but also a fascinating tale of how our understanding of stellar measurements can evolve and change as our observational techniques become more sophisticated. For nearly a decade, Scuti reigned supreme in the cosmic size hierarchy, with measurements suggesting a radius of approximately 1,908 times that of our Sun. To visualize this scale, imagine placing Scuti at the center of our solar system. Its bloated outer atmosphere would extend well beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, and Mars in its glowing embrace. The scale is so vast that light itself would take several hours to travel from the star's center to its outer edge, a journey that takes light only 2.3 seconds to complete for our own Sun. The discovery and initial measurement of Scuti's enormous size represented a triumph of modern observational astronomy. Using sophisticated techniques to measure the star's brightness, temperature, and distance, astronomers calculated that this stellar giant possessed a volume roughly 5 billion times greater than our Sun. It was a measurement that captured the public imagination and cemented Scuti's place in popular astronomy as the definitive example of stellar gigantism. But science is a self-correcting endeavor, and the story of Scuti provides a perfect example of how new data can dramatically revise our understanding of cosmic objects. The revolution came with the European Space Agency's Gaia mission, a space-based observatory designed to measure the precise positions and distances of over 1 billion stars in our galaxy. When Gaia's incredibly precise measurements were applied to Scuti, they revealed that the star was actually closer to Earth than previously thought. This might seem like a minor technical adjustment, but in the world of stellar astronomy, distance measurements are absolutely crucial for determining a star's physical properties. If a star is closer than we initially calculated, it means the star doesn't need to be as large or as luminous to appear as bright as it does in our telescopes. The revised distance measurements from Gaia forced astronomers to recalculate Scuti's size, and the results were dramatically different from the original estimates. The new measurements suggested that Scuti has a radius of approximately 755 times that of our Sun, still enormous by any standard, but roughly half the size of the original estimates. This revision knocked Scuti from its throne as the largest known star, demonstrating how the pursuit of astronomical knowledge is an ongoing process of refinement and discovery. What seemed like a settled question became open for debate once again, highlighting the dynamic nature of scientific understanding. Despite losing its title as the largest star, Scuti remains a fascinating object that provides crucial insights into the physics of stellar evolution and the behavior of the most massive stars in our galaxy. The star's surface temperature of approximately 3,165 degrees Kelvin places it firmly in the category of cool stars, giving it the characteristic deep red color that defines red supergiants. This relatively low temperature, combined with the star's enormous surface area, results in a total luminosity that is still roughly 340,000 times greater than our Sun. The physics behind Scuti's enormous size involves the same fundamental processes that govern all red supergiants, but pushed to extreme limits. The star began its life as a massive main sequence star, likely 25 to 40 times more massive than our Sun. During its main sequence phase, it would have been a hot, blue star, burning hydrogen in its core at prodigious rates and shining with intense ultraviolet radiation. As the hydrogen fuel in the core became depleted, Scuti began the evolutionary transformation that led to its current gigantic state. The core contracted and heated up, while nuclear burning began in shells surrounding the inert core. This shell burning provided the energy needed to inflate the star's outer layers to their current enormous dimensions, creating the bloated structure we observe today. The age of Scuti provides another fascinating aspect of its story. Despite its enormous size and the impression of ancient stability it might convey, Scuti is actually a relatively young star by astronomical standards. Current estimates suggest it may be only 10 to 20 million years old, making it roughly 200 times younger than our 4.6 billion-year-old Sun. This youth is characteristic of all massive stars, which burn through their nuclear fuel so rapidly that their entire lifespans are compressed into what amounts to a cosmic instant. The rapid evolution of massive stars like Scuti has profound implications for understanding stellar populations and galactic evolution. While stars like our Sun can shine steadily for billions of years, providing stable energy sources for the development of planetary systems and potentially life, massive stars like Scuti live fast and die young. Their brief but spectacular lives end in supernova explosions that can briefly outshine entire galaxies and scatter heavy elements across vast regions of space. The variability of Scuti adds another layer of complexity to its character. Like many red supergiants, Scuti is not a constant star, but undergoes regular fluctuations in brightness over periods of several years. These variations are caused by pulsations in the star's outer layers, driven by the complex interplay between radiation pressure, gravity, and the opacity of the stellar material. During these pulsation cycles, the star's radius can change by hundreds of millions of kilometers, making precise size measurements even more challenging. The stellar wind from Scuti represents another extreme aspect of this stellar giant's behavior. Red supergiants are known for their powerful stellar winds, streams of charged particles that flow away from the star at velocities of hundreds of kilometers per second. Scuti's wind is particularly intense, carrying away mass equivalent to roughly one Earth every few thousand years. Over the star's lifetime, this mass loss will significantly reduce its total mass and enrich the surrounding interstellar medium with heavy elements. The location of Scuti within our galaxy provides important context for understanding both the star itself and the broader processes of massive star formation. Situated in the constellation Scutum, Scuti lies in the direction of our galaxy's center, in a region rich with massive stars and active star formation. This location is not coincidental, as the most massive stars tend to form in regions where there are abundant supplies of the gas and dust needed for star formation. The study of Scuti has been greatly aided by advances in infrared astronomy, which allow astronomers to peer through the cosmic dust that obscures much of the galactic center region at visible wavelengths. Infrared observations reveal not only the star itself, but also the complex environment of gas and dust that surrounds it, created by millions of years of mass loss through stellar winds. The spectroscopic analysis of Scuti's light reveals the complex chemistry occurring in the star's atmosphere. The spectrum shows strong absorption lines from various molecular species, including titanium oxide and water vapor, which can only exist at the relatively cool temperatures found in red supergiant atmospheres. These molecular features provide crucial information about the star's temperature, composition, and the physical conditions in its extended atmosphere. The future evolution of Scuti is written in the laws of stellar physics. As a massive red supergiant, the star is approaching the final phases of its evolutionary journey. The nuclear processes in its core are becoming increasingly unstable as the star attempts to burn ever heavier elements to maintain the energy output needed to support its enormous structure. Eventually, the star will reach a point where no further nuclear fusion can sustain it against gravitational collapse. When that moment arrives, Scuti will likely explode as a supernova, an event so energetic that it will briefly outshine all the other stars in our galaxy combined. The explosion will be visible from thousands of light years away and will scatter the heavy elements created in the star's core across vast regions of space. These elements, forged in the nuclear furnace of a dying giant, will eventually become incorporated into future generations of stars and planets, continuing the cosmic cycle of stellar death and rebirth. The story of Scuti also illustrates the importance of continued observation and measurement in astronomy. The revision of its size based on improved distance measurements demonstrates that our understanding of even well-studied objects can change as our techniques become more sophisticated. This ongoing process of refinement and discovery is what makes astronomy such a dynamic and exciting field of study. As we contemplate Scuti in all its magnificent enormity, we're reminded that even after losing its title as the largest known star, it remains an object of extraordinary scale and beauty. This stellar giant, with its deep red glow and pulsating variability, represents one of the universe's most spectacular examples of how matter can organize itself into structures of almost incomprehensible size and complexity. The legacy of Scuti extends beyond its physical properties to its role in capturing public interest in astronomy and stellar physics. For years, it served as the go-to example when astronomers wanted to illustrate the incredible diversity of stellar sizes and the extreme objects that exist in our universe. Even with revised measurements, it continues to inspire wonder and curiosity about the cosmos and our place within it. Our final stellar giant takes us on a journey to one of the most intensively studied massive stars in our galaxy, a cosmic behemoth that has captivated astronomers for decades with its extreme characteristics and complex behavior. This is Canis Majoris, a red hypergiant located approximately 3,900 light-years from Earth in the constellation Canis Major, the Great Dog, where it shines as one of the most luminous and structurally complex stars ever observed. Canis Majoris occupies a special place in the pantheon of stellar giants, not just because of its enormous size, but because of the extraordinary way it interacts with its surrounding environment. With a radius estimated at roughly 1,720 times that of our Sun, this star would extend well beyond the orbit of Saturn if placed at the center of our solar system. But what truly sets VY Canis Majoris apart from other giant stars is the spectacular light show it creates as it slowly destroys itself through one of the most dramatic mass loss processes ever observed. Imagine a star so violent in its death throes that it literally tears itself apart, ejecting massive chunks of its own substance into space with such force that these expelled fragments glow like cosmic fireworks for thousands of years. This is the reality of VY Canis Majoris, a star that has been compared to Betelgeuse on steroids, displaying mass loss behavior so extreme that it challenges our understanding of how the largest stars can maintain their structural integrity. The luminosity of VY Canis Majoris represents another extreme in stellar physics. This single star shines with the combined light of approximately 300,000 suns, making it one of the most luminous objects in our entire galaxy. To put this incredible brightness in perspective, if VY Canis Majoris were placed at the same distance from Earth as our nearest stellar neighbor, it would appear roughly 10,000 times brighter than Venus at its most brilliant, easily visible during the day and casting shadows at night. But perhaps the most remarkable aspect of VY Canis Majoris isn't its size or brightness, but the incredible complexity of the structures it has created in the space around it. Over the course of its relatively brief lifetime, this stellar giant has ejected enormous amounts of material in a series of dramatic outbursts, creating a complex asymmetric envelope of gas and dust that extends for several light years in all directions. This circumstellar envelope represents a cosmic art gallery, filled with knots, arcs, and filaments of glowing material that tell the story of the star's violent recent history. The mass loss rate from VY Canis Majoris is extraordinary even by the standards of red hypergiants. During its most active periods, the star can lose mass equivalent to our entire Earth every few years, a rate so extreme that it would strip away Jupiter's worth of material in just a few centuries. But what makes this mass loss even more remarkable is that it doesn't occur as a steady stellar wind. Instead, VY Canis Majoris undergoes periodic outbursts where it ejects massive amounts of material in violent episodes that can last for years or even decades. These mass ejection events are so energetic that they create discrete knots and clumps of material that travel outward from the star at velocities of hundreds of kilometers per second. Some of these ejected fragments contain more mass than twice that of Jupiter, representing truly enormous quantities of stellar material hurled into space by processes that we're only beginning to understand. The ejected material glows brightly as it's heated by radiation from the central star, creating the spectacular nebula structures that make VY Canis Majoris one of the most visually striking objects in the infrared sky. The temperature of VY Canis Majoris's surface, approximately 3,490 degrees Kelvin, places it among the coolest of the red hypergiants, giving it a deep red color that belies its incredible energy output. This relatively low temperature is characteristic of stars in the final phases of their evolution, when their outer layers have expanded to enormous dimensions and cooled accordingly. The combination of low temperature and enormous surface area creates the perfect conditions for the formation of complex molecules in the star's atmosphere, including water vapor, silicon monoxide, and various metallic compounds. The discovery and study of molecular masas around VY Canis Majoris has provided astronomers with unprecedented insights into the structure and dynamics of the star's immediate environment. Masas are the microwave equivalent of lasers, occurring when specific molecules in space are excited to produce coherent radiation at precise frequencies. VY Canis Majoris was one of the first stars where such masas were detected, and the detailed mapping of these mesa emissions has revealed the three-dimensional structure of the gas flows around the star with remarkable precision. The massa emissions from water, silicon monoxide, and other molecules create a kind of cosmic GPS system that allows astronomers to trace the motion of material as it flows away from the star. These observations have revealed that the mass loss from VY Canis Majoris is highly asymmetric, with material being ejected preferentially in certain directions, while other regions around the star remain relatively quiet. This asymmetry suggests that the star's mass loss is influenced by factors we don't yet fully understand, possibly including magnetic fields, rotation, or even the presence of unseen companions. The evolutionary status of VY Canis Majoris places it among the most massive stars ever formed in our galaxy. Current estimates suggest that when it first formed, this star may have had an initial mass of 30 to 40 times that of our Sun. Such massive stars represent the upper end of what stellar formation processes can create, and they play crucial roles in the chemical evolution of galaxies despite their relative rarity. The nuclear processes occurring in the core of VY Canis Majoris represent some of the most extreme conditions that can exist in stable matter. The core temperature likely exceeds 100 million degrees Kelvin, hot enough to fuse silicon into iron and other heavy elements through a complex series of nuclear reactions. These processes release enormous amounts of energy, but they also mark the beginning of the end for the star, as iron cannot be fused to release further energy. The pulsational behavior of VY Canis Majoris adds another layer of complexity to this already remarkable star. Like many red hypergiants, it undergoes irregular variations in brightness over periods ranging from months to years. These variations are caused by changes in the star's size and temperature, as its outer layers expand and contract in response to the variable energy output from the core. During some of these pulsation cycles, the star can dim by factors of 5 or 6, becoming temporarily hidden behind clouds of dust created by its own mass loss. The study of VY Canis Majoris has been revolutionized by advances in high-resolution imaging techniques that allow astronomers to resolve details in the star's circumstellar environment with unprecedented clarity. These observations have revealed a wealth of structures, including bipolar jets, spiral patterns, and discrete clumps of material that provide clues about the physical processes driving the star's mass loss. Each new observation adds pieces to the puzzle of understanding how the most massive stars end their lives. The chemical composition of the material being ejected by VY Canis Majoris tells the story of nuclear processes that have occurred throughout the star's lifetime. Spectroscopic analysis reveals the presence of heavy elements, including carbon, oxygen, silicon, and iron, all created in the star's nuclear furnace and now being dispersed into the surrounding interstellar medium. This material will eventually be incorporated into future generations of stars and planets, contributing to the ongoing chemical evolution of our galaxy. The location of VY Canis Majoris within the galactic disk provides important context for understanding its formation and evolution. The star lies in a region rich with massive stars and active star formation, suggesting it formed as part of a larger stellar association or cluster. Many of its original siblings have likely already evolved and exploded as supernovae, leaving VY Canis Majoris as one of the last survivors of its stellar generation. The future of VY Canis Majoris is written in the fundamental laws of stellar physics. As the nuclear fuel in its core becomes exhausted, the star will face an inevitable gravitational collapse that will trigger one of the most energetic events in the universe. The resulting supernova explosion will briefly outshine all the other stars in our galaxy and will be visible from thousands of light years away. The shock waves from this explosion will compress nearby interstellar gas, potentially triggering the formation of new stars and continuing the cosmic cycle of stellar death and birth. The legacy of VY Canis Majoris extends far beyond its physical properties to its role in advancing our understanding of stellar evolution and the life cycles of the most massive stars. The detailed studies of this star have provided crucial insights into the processes that govern mass loss in red hypergiants, the formation of complex circumstellar structures, and the chemical enrichment of galaxies through stellar winds and supernova explosions. As we contemplate VY Canis Majoris in all its violent magnificence, we're witnessing one of the universe's most spectacular ongoing experiments in stellar physics. This star represents the ultimate expression of stellar gigantism, a cosmic giant that has pushed the boundaries of size, luminosity, and mass loss to their absolute limits. Its complex behavior and dramatic variability remind us that the largest stars in the universe are not stable, eternal objects, but dynamic, evolving systems that can undergo dramatic changes over relatively short periods. The story of VY Canis Majoris also illustrates the incredible diversity that exists among stellar giants. While all massive stars follow similar evolutionary paths, each one is unique in its specific characteristics and behavior. The asymmetric mass loss, the complex circumstellar structures, and the extreme variability of VY Canis Majoris make it a one-of-a-kind object that continues to surprise astronomers with each new observation. The ongoing study of VY Canis Majoris and other red hypergiants is crucial for understanding the final fates of the most massive stars and their roles in galactic evolution. These stars are the primary sources of heavy elements in the universe, and their explosive deaths as supernovae can trigger waves of star formation that propagate through galaxies for millions of years. Understanding their behavior is essential for comprehending how galaxies evolve and how the chemical elements necessary for planets and life are distributed throughout the cosmos. As we stand at the threshold of new astronomical discoveries with next-generation telescopes and instruments coming online, VY Canis Majoris will undoubtedly continue to reveal new secrets about the nature of stellar giants. Each observation brings us closer to understanding the complex physics that govern these remarkable objects and their crucial roles in the grand story of cosmic evolution. The 5 stellar giants we've encountered on this cosmic journey represent more than just impressive numbers and measurements. They are windows into the fundamental processes that shape our universe, laboratories where matter and energy interact under conditions so extreme that they push the boundaries of our theoretical understanding. From the theoretical enormity of Stevenson 2·18 to the luminous power of W26, from the dynamic evolution of WOH G64 to the former champion UY Scuti, and finally to the spectacular complexity of VY Canis Majoris, each of these stars tells a unique story about the incredible diversity and beauty that exists in the cosmos. These stellar giants remind us that we live in a universe of unimaginable scale and complexity, where objects exist that dwarf our everyday experience and challenge our ability to comprehend their true nature. They are cosmic beacons that have been shining across vast distances of space and time, carrying messages about the fundamental laws of physics and the processes that govern stellar evolution. As you drift toward rest tonight, perhaps gazing up at the gentle points of light scattered across your local sky, remember that among those distant suns may be giants beyond imagination. Stars so large that they could swallow entire solar systems, so bright that they outshine hundreds of thousands of normal stars, so complex that they create their own cosmic weather systems of gas and dust spanning light years of space. The story of these stellar giants is ultimately our story too, for we are made of elements forged in the nuclear furnaces of such massive stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in the cores of dying giants and scattered across space in their final explosive moments. We are quite literally made of star stuff, temporary arrangements of cosmic material that have achieved the remarkable ability to contemplate our own origins. In understanding these magnificent stellar giants, we glimpse something profound about the nature of existence itself. We see how the universe transforms simple hydrogen and helium into structures of breathtaking complexity and beauty, how gravity and nuclear physics collaborate to create objects that exist on scales almost beyond human comprehension, and how even the largest and most powerful stars must eventually yield to the inexorable passage of time. The universe has a way of humbling us just when we think we understand its rules. As we've journeyed through these 5 cosmic titans, we've discovered that measuring the largest stars isn't just about pointing telescopes at distant points of light and calculating numbers. It's about pushing against the very boundaries of human knowledge, wrestling with uncertainties that span hundreds of solar radii, and accepting that some of the most fundamental questions about stellar physics remain tantalizingly out of reach. Each of these stellar giants exists in a realm where normal physics becomes extraordinary, where the familiar laws that govern our earthly experience are stretched to their absolute limits. The temperatures in their cores exceed anything we can create in our most powerful laboratories. The pressures at their centers would crush atomic nuclei together with forces that dwarf the strongest materials known to science. The magnetic fields threading through their atmospheres could power entire civilizations for millennia. Yet for all their incredible power and scale, these stars share a common destiny written in the fundamental equations of stellar evolution. They are all approaching the same inevitable endpoint, the moment when the nuclear fires that have sustained them for millions of years can no longer hold back the relentless pull of gravity. When that moment arrives, each will face the ultimate test of physics, a catastrophic collapse that will either tear them apart in spectacular supernova explosions or compress them into objects even more exotic than the giants they once were. The mass loss we've observed from stars like VY Canis Majoris and WOH G64 represents more than just stellar wind. It's the universe's way of recycling the heavy elements created in stellar cores, distributing the building blocks of planets and life across vast regions of space. Every atom of carbon, oxygen, and iron being expelled from these dying giants will eventually find its way into future generations of stars, planets, and perhaps even living beings. This cosmic recycling process operates on timescales that stretch human imagination. The material being ejected from these stars today may not be incorporated into new stellar systems for millions or even billions of years. Yet the process is inexorable, driven by the fundamental forces that govern how matter behaves under extreme conditions. The heavy elements that make our existence possible were once locked in the cores of similar stellar giants, released only when those ancient stars reached the end of their evolutionary journey. The variability we observe in these massive stars tells us something profound about the nature of stellar stability. Unlike our Sun, which has maintained relatively steady energy output for billions of years, these giants exist in states of barely controlled chaos. Their brightness can change by factors of 5 or 10 over periods of months or years, driven by pulsations that cause their outer layers to expand and contract like cosmic balloons. These pulsations are symptoms of the internal struggles occurring within the stars. As different nuclear burning processes ignite and extinguish in their cores, the energy output fluctuates wildly. The star's outer layers respond to these changes by swelling and shrinking, creating the irregular variability that makes precise measurements so challenging. It's as if we're trying to measure the size of a soap bubble while someone is blowing on it from different directions. The theoretical limits we've discussed, the maximum sizes that stellar physics allows, represent more than just mathematical curiosities. They reflect fundamental constraints on how matter can organize itself in the universe. Stars that grow too large become gravitationally unstable, unable to maintain the delicate balance between radiation pressure pushing outward and gravity pulling inward. They either shed their outer layers through violent mass loss or collapse under their own weight. The Hayashi limit and other theoretical boundaries serve as cosmic speed limits for stellar evolution, ensuring that the universe remains a stable and predictable place despite the extreme conditions that exist within the largest stars. These limits arise from the basic properties of matter and energy, from the way atoms absorb and emit radiation, from the mechanics of nuclear fusion, and from the curvature of space-time itself. Yet even as we map these theoretical boundaries, we continue to discover stars that seem to push against them. Stevenson 2-18, with its possibly exaggerated size, reminds us that our understanding of stellar physics may still be incomplete. Perhaps there are processes occurring in the most extreme stars that we haven't yet discovered, mechanisms that allow matter to organize itself in ways we haven't imagined. The environments surrounding these stellar giants create some of the most complex structures in the known universe. The circumstellar envelopes around stars like VY Canis Majoris contain more intricate patterns than the most elaborate human artwork, sculpted by forces that operate on scales spanning light years. These structures form and evolve over thousands of years, shaped by stellar winds, radiation pressure, magnetic fields, and gravitational forces that interact in ways we're only beginning to understand. The discovery of ionized nebulae around red supergiants like W26 has forced astronomers to reconsider their assumptions about how these stars interact with their surroundings. The fact that relatively cool stars can create regions of ionized gas extending for light years suggests that our models of stellar atmospheres and mass loss processes need significant revision. It's a reminder that even the most well-studied objects in the universe can still surprise us with unexpected behavior. The binary nature of systems like WOHG64 adds yet another layer of complexity to the story of stellar giants. The gravitational dance between massive stars and their companions can dramatically affect their evolution, creating asymmetric mass loss patterns, triggering unusual variability, and potentially influencing the timing and nature of their eventual explosive deaths. Understanding these interactions requires sophisticated computer models that account for the complex interplay of gravity, radiation, and magnetic fields in systems where the primary star may be 1,000 times larger than our Sun. The role of metallicity, the abundance of heavy elements relative to hydrogen and helium, emerges as a crucial factor in determining how large stars can grow. The lower metallicity environment of the Large Magellanic Cloud, where WOHG64 resides, may allow stars to reach sizes that would be impossible in our own galaxy. Heavy elements affect how efficiently stars can radiate energy away from their surfaces, influencing the balance between radiation pressure and gravity that determines a star's maximum size. This metallicity dependence has profound implications for understanding stellar evolution in the early universe, when heavy elements were much rarer than they are today. The first generation of stars formed from pristine hydrogen and helium, may have been able to grow to sizes that dwarf even the giants we've discussed. These hypothetical population 3 stars could have been thousands of times more massive than our Sun, shining with the light of entire galaxies before collapsing into the first black holes. The observational challenges involved in studying these stellar giants highlight the incredible advances that have occurred in astronomical instrumentation over the past few decades. The ability to measure stellar sizes with interferometry, to map circumstellar structures with high-resolution imaging, and to track variability over extended periods, represents a triumph of human ingenuity and technological development. Yet even our most sophisticated instruments struggle to capture the full complexity of these objects. The dusty environments around many red supergiants obscure them at visible wavelengths, requiring observations in the infrared where the warm dust glows brightly. The irregular variability of many giants makes it difficult to establish their average properties, as measurements taken at different times can yield significantly different results. The future of stellar giant research lies in the development of even more advanced observational techniques and theoretical models. Space-based interferometers may eventually allow us to resolve the surfaces of these distant stars directly, revealing details about their structure and evolution that are currently hidden from view. Advanced computer simulations incorporating three-dimensional magnetohydrodynamics may help us understand the complex processes that drive mass loss and variability in the largest stars. The study of gravitational waves from stellar core collapse may provide new insights into the final moments of stellar giants, revealing details about the physical processes that occur during supernova explosions. As our detectors become more sensitive, we may be able to observe the gravitational wave signatures of stellar giants as they undergo the catastrophic collapse that marks the end of their lives. The connection between stellar giants and the formation of the heaviest elements in the universe represents one of the most important aspects of their cosmic role. The process, nucleosynthesis, that occurs during supernova explosions and neutron star mergers is responsible for creating roughly half of the elements heavier than iron. Understanding how the most massive stars evolve and explode is crucial for comprehending how these elements are produced and distributed throughout the cosmos. The impact of stellar giants on their galactic environments extends far beyond their immediate surroundings. The shockwaves from supernova explosions can propagate through interstellar space for millions of years, compressing gas clouds and triggering new episodes of star formation. The heavy elements they scatter enrich the interstellar medium, gradually increasing the metallicity of their host galaxies and enabling the formation of planetary systems capable of supporting complex chemistry and life. The rarity of these stellar giants makes each one precious for astronomical study. With only a few dozen confirmed red supergiants and hypergiants in our galaxy, every observation provides crucial data for understanding stellar evolution. The loss of any one of these stars to supernova explosion represents the end of a unique natural laboratory where extreme physics plays out on cosmic scales. The cultural impact of stellar giants extends beyond the scientific community to capture the imagination of anyone who has ever wondered about the scale of the universe. These stars serve as powerful reminders of humanity's place in the cosmic hierarchy, demonstrating that we exist in a universe filled with objects that dwarf our everyday experience. They inspire humility while simultaneously filling us with wonder at the incredible diversity and beauty that exists in the cosmos. The philosophical implications of stellar giants touch on fundamental questions about the nature of existence and our relationship to the universe. If stars thousands of times larger than our Sun can exist for only brief moments in cosmic time, what does that tell us about permanence and impermanence? If the elements in our bodies were forged in the cores of such giants, what does that reveal about our connection to the cosmos? As we continue to discover new stellar giants and refine our measurements of known ones, we're constantly reminded that the universe is far stranger and more wonderful than our ancestors could have imagined. Each new observation adds to our understanding, while simultaneously revealing new mysteries to be solved. The study of stellar giants represents one of the most active and exciting frontiers in modern astronomy, where theoretical physics meets observational astronomy in the pursuit of understanding the most extreme objects in the universe. The technological advances required to study these distant giants have driven innovations that benefit many other areas of astronomy and even everyday life. The interferometric techniques developed to measure stellar sizes have applications in everything from studying exoplanets to improving GPS accuracy. The infrared detectors designed to peer through cosmic dust have found uses in medical imaging and environmental monitoring. The international cooperation required for major astronomical projects studying stellar giants demonstrates how scientific curiosity can unite humanity in common purpose. When astronomers from around the world collaborate to observe a stellar giant using telescopes scattered across multiple continents, they're participating in one of humanity's most noble endeavors, the quest to understand our place in the cosmos. The educational value of stellar giants cannot be overstated. These objects provide concrete examples of abstract physical concepts, making ideas like nuclear fusion, stellar evolution, and the formation of heavy elements tangible and accessible. When students learn that the iron in their blood was forged in the core of a dying star thousands of times larger than the Sun, they gain a visceral understanding of their connection to the universe that no textbook can provide. The ongoing debate about which star truly deserves the title of largest reminds us that science is not a collection of fixed facts, but a dynamic process of discovery and revision. As our instruments improve and our understanding deepens, we must be prepared to revise our conclusions and embrace new paradigms. The dethronement of Scuti and the uncertainties surrounding Stevenson 2-18 demonstrate that even well-established scientific facts are subject to revision when new evidence emerges. The future discoveries awaiting us in the realm of stellar giants promise to be even more extraordinary than what we've already found. As space-based telescopes push deeper into the universe and ground-based instruments achieve ever higher resolution, we may discover stars that dwarf even the giants we've discussed tonight. The universe has consistently surprised us with its capacity for creating objects more extreme than we thought possible. And there's every reason to believe that trend will continue. The legacy of our current knowledge about stellar giants will be measured not just in the specific facts we've uncovered, but in the questions we've learned to ask and the methods we've developed to answer them. Each generation of astronomers builds upon the work of their predecessors, pushing the boundaries of knowledge ever outward into the cosmic unknown. As we reach toward the conclusion of our stellar odyssey, we find ourselves transformed by the journey we've undertaken together. We began with simple questions about size and scale, but we've discovered that understanding stellar giants requires grappling with some of the most fundamental aspects of physics and cosmology. These stars are not just large objects floating in space, they're cosmic laboratories where matter and energy interact under conditions that test the limits of our theoretical understanding. The story of stellar giants is ultimately a story about the universe itself, about how simple ingredients like hydrogen and helium can be transformed through the action of gravity and nuclear physics into structures of breathtaking complexity and beauty. It's a story about cycles of birth, death, and rebirth that play out over millions of years, enriching the cosmos with the heavy elements necessary for planets and life. But perhaps most importantly, it's a story about human curiosity and our relentless drive to understand the universe around us. The fact that creatures evolved on a small rocky planet orbiting an ordinary star can contemplate objects thousands of times larger than their sun, located thousands of light years away, represents one of the most remarkable achievements in the history of life itself. The stellar giants we've encountered tonight will continue their cosmic dance long after we're gone, pulsing and varying, losing mass and evolving, gradually approaching their inevitable explosive endings. But the knowledge we've gained about them, the understanding we've developed of their nature and behavior, will endure as part of humanity's growing comprehension of the universe we inhabit. In contemplating these cosmic titans, we glimpse something profound about the nature of existence itself. We see how the universe operates on scales that stretch human imagination, how beauty and complexity can emerge from the interplay of fundamental forces, and how even the largest and most powerful objects must eventually yield to the passage of time. We are reminded that we are part of something far grander than ourselves, participants in a cosmic story that began with the Big Bang and will continue long after our sun has become a white dwarf. Tonight, as you settle into rest, perhaps you'll find yourself looking up at the stars with new eyes, knowing that among those distant points of light may lurk giants beyond imagination. Stars so large they could engulf entire solar systems, so bright they outshine hundreds of thousands of normal stars, so complex they create their own weather systems spanning light years of space. And in that knowledge, you might find both humility at the scale of the cosmos and wonder at humanity's ability to comprehend such magnificent objects through the power of science and imagination. The universe of stellar giants awaits further exploration, promising discoveries that will continue to challenge our understanding and inspire our sense of wonder for generations to come. The measurement challenges we face with these stellar giants reveal something profound about the nature of scientific discovery itself. When we attempt to determine the precise size of a star located thousands of light years away, we're essentially trying to measure the width of a coin from a distance of several thousand miles. Except that coin is glowing, pulsating, and surrounded by clouds of its own making. The uncertainties involved aren't just technical limitations, they're fundamental constraints imposed by the vast scales of space and time that separate us from these cosmic behemoths. Consider the complex dance of variables that astronomers must account for when measuring stellar radii. The star's distance from Earth, often uncertain by tens of percent, directly affects all subsequent calculations. The effective temperature of the stellar surface, derived from spectroscopic analysis, carries its own margins of error. The total luminosity, calculated from the star's apparent brightness and distance, multiplies these uncertainties. When these measurements are combined through the Stefan-Boltzmann law to determine radius, small errors in any component can lead to dramatically different size estimates. This intricate web of measurement dependencies explains why stellar size rankings can shift so dramatically with improved observations. The revision of Scuti's size wasn't due to the star itself changing, but to our refined understanding of its distance courtesy of the Gaia space mission. Such revisions remind us that the pursuit of astronomical knowledge is an ongoing process of refinement, where today's certainties may become tomorrow's footnotes in the ever-evolving story of cosmic understanding. The theoretical frameworks that govern stellar structure add another layer of complexity to interpreting these measurements. When we encounter stars like Stevenson 218 that appear to exceed theoretical size limits, we face a fundamental question about the nature of scientific knowledge. Are our theoretical models incomplete, missing crucial physics that would allow such extreme objects to exist? Or are the observational challenges so severe that we're seeing mirages in the cosmic data, apparent giants that dissolve under more careful scrutiny? The answer likely lies somewhere between these extremes, in the messy reality where theory and observation must constantly negotiate with each other. Stellar evolution models are built upon our best understanding of nuclear physics, thermodynamics, and stellar structure, but they necessarily make simplifying assumptions about complex three-dimensional processes. Real stars don't always behave according to the elegant equations in textbooks, especially when they're pushed to the absolute limits of what stellar physics allows. The temporal aspect of stellar giant behavior adds yet another dimension to these measurement challenges. Unlike solid objects with fixed dimensions, these stars are dynamic systems that can change their size significantly over periods ranging from months to decades. The pulsational variability observed in many red supergiants means that asking for their exact radius is somewhat like asking for the exact size of a heartbeat. The answer depends critically on when you make the measurement and how you define the boundaries of the phenomenon you're studying. This variability isn't just an inconvenience for astronomers trying to make precise measurements. It's a window into the fundamental physics occurring within these stellar giants. The regular pulsations observed in some stars reflect the complex interplay between radiation pressure, gravity, and the opacity of stellar material as it heats and cools. Irregular variations, like those seen in VY Canis Majoris during its dramatic outbursts, suggest that the internal structure has become chaotic and unstable, driven by competing nuclear processes that are no longer in equilibrium. The circumstellar environment surrounding these stellar giants create additional observational challenges while revealing the incredible complexity of stellar mass loss processes. The dust and gas expelled by these stars can both obscure and reveal different aspects of their behavior, depending on the wavelength of observation. What appears as a simple point of light in visible wavelengths transforms into an intricate landscape of shells, knots, and filaments when observed in the infrared, where the warm dust glows brightly against the cosmic background. These extended envelopes of expelled material tell stories that span thousands of years of stellar evolution. Each shell and arc represents a different episode of mass loss, a moment when the star's internal struggles manifested as violent expulsion of its outer layers. By mapping these structures in detail, astronomers can reconstruct the recent history of stellar giants, understanding how their mass loss rates have varied over time and what physical processes drove these variations. The chemical composition of this expelled material provides crucial insights into the nuclear processes occurring within stellar cores. Spectroscopic analysis reveals not just the presence of heavy elements like carbon, oxygen, and silicon, but their relative abundances and isotopic ratios. These chemical fingerprints tell us about the specific nuclear reactions that created these elements, the temperatures and pressures required for their formation, and the mixing processes that brought them from the stellar core to the surface where they could be expelled into space. The role of magnetic fields in shaping the behavior of stellar giants represents one of the most active areas of current research. While magnetic fields are difficult to measure directly in distant stars, their effects can be inferred from the asymmetric patterns of mass loss and the complex structures observed in circumstellar envelopes. Strong magnetic fields can channel stellar winds into narrow jets or create preferential directions for mass ejection. explaining why many stellar giants are surrounded by highly asymmetric nebulae rather than simple spherical shells. The interaction between stellar rotation and magnetic fields creates additional complications for understanding stellar giant behavior. As massive stars evolve and expand, conservation of angular momentum should cause them to spin more slowly, but the actual rotation rates observed in many giants suggest that internal processes are redistributing angular momentum in ways we don't fully understand. The coupling between rotation, magnetic fields, and mass loss may be crucial for determining how large these stars can grow and how they ultimately meet their explosive ends. The binary nature of many stellar systems adds yet another variable to the already complex physics of stellar giants. When a red supergiant like WOH G64 has a close companion, the gravitational interaction can significantly affect the primary star's evolution. Material flowing from the giant toward its companion can create accretion disks, produce unusual spectral signatures, and potentially influence the timing and nature of the primary star's eventual supernova explosion. These binary interactions can also affect the mass loss characteristics of stellar giants in ways that are only beginning to be understood. The gravitational influence of a companion can create tidal distortions in the primary star's outer layers, potentially triggering enhanced mass loss episodes or creating asymmetric wind patterns. Understanding these effects is crucial for interpreting observations of stellar giants and for predicting their future evolution. The metallicity dependence of stellar giant properties emerges as a crucial factor in understanding how these objects behave in different galactic environments. The abundance of heavy elements in a star's atmosphere affects its opacity, which in turn influences how efficiently energy can be transported from the core to the surface. Stars with lower metallicity may be able to grow larger before becoming unstable, potentially explaining why some of the most extreme stellar giants are found in the metal-poor environment of the Large Magellanic Cloud. This metallicity effect has profound implications for understanding stellar evolution in the early universe, when heavy elements were much rarer than they are today. The first generation of massive stars, formed from pristine hydrogen and helium, may have been able to reach sizes that dwarf even the giants we observe today. These hypothetical population 3 stars could have been instrumental in enriching the early universe with heavy elements and in forming the first black holes through direct collapse. The observational techniques used to study stellar giants continue to evolve rapidly, driven by advances in detector technology, interferometric methods, and space-based observations. The ability to combine observations from multiple telescopes using very long baseline interferometry allows astronomers to achieve angular resolutions that would require single telescopes hundreds of kilometers in diameter. These techniques are pushing toward the ultimate goal of directly imaging the surfaces of stellar giants, revealing details about their structure and variability that are currently hidden from view. Future space-based interferometers may eventually allow astronomers to watch stellar giants evolve in real time, observing how their surfaces change during pulsation cycles and mass loss episodes. Such observations would provide unprecedented insights into the physical processes that govern these extreme objects and would allow direct tests of theoretical models that are currently based on indirect evidence. The role of stellar giants in galactic chemical evolution represents one of the most important aspects of their cosmic significance. These stars are the primary factories for elements heavier than oxygen, creating them through nuclear fusion processes that occur only under the extreme conditions found in massive stellar cores. When these giants eventually explode as supernovae, they scatter these heavy elements across vast regions of space, gradually enriching the interstellar medium with the building blocks necessary for planet formation and the development of complex chemistry. The efficiency of this chemical enrichment process depends critically on understanding the mass loss rates and explosion mechanisms of stellar giants. Stars that lose too much mass during their giant phase may not retain enough material to produce energetic supernova explosions, instead ending their lives as relatively faint electron capture supernova, or even collapsing directly to black holes without significant element dispersal. Understanding these pathways is crucial for modeling how galaxies evolve chemically over cosmic time. The connection between stellar giants and gamma-ray bursts represents another frontier in high-energy astrophysics. Some theoretical models suggest that the most massive stellar giants, particularly those with rapid rotation and strong magnetic fields, may be the progenitors of long-duration gamma-ray bursts when they collapse to form black holes. These explosions are among the most energetic events in the universe, briefly outshining entire galaxies and potentially affecting the evolution of life on planets located thousands of light years away. The search for the descendants of stellar giants provides another avenue for understanding these extreme objects. The neutron stars and black holes formed when stellar giants collapse carry information about their progenitor stars encoded in their masses, spins, and orbital characteristics when they exist in binary systems. By studying these compact remnants, astronomers can work backward to understand the properties of the stellar giants that created them. The gravitational wave detections from merging neutron stars and black holes are beginning to provide new insights into the final fates of stellar giants. The masses and merger rates of these compact objects constrain models of stellar evolution and help determine what fraction of stellar giants end their lives in different types of explosions. As gravitational wave detectors become more sensitive, they may even be able to observe the core collapse events themselves, providing direct information about the final moments of stellar giant evolution. The impact of stellar giants on their local environments extends far beyond the immediate effects of their stellar winds and eventual explosions. The intense radiation from these luminous stars can ionize gas clouds over distances of hundreds of light years, creating vast H2 regions that glow with the characteristic red light of hydrogen emission. These ionized regions can persist for millions of years after the stellar giants that created them have exploded, serving as monuments to their former presence. The shock waves from supernova explosions propagate through the interstellar medium for even longer periods, creating superbubbles of hot, rarefied gas that can extend for thousands of light years. These structures affect the dynamics of entire galactic regions, influencing how gas flows between the galactic disk and halo, and potentially regulating the rate of star formation over vast areas. The study of stellar giants in other galaxies provides crucial tests of our understanding of stellar evolution under different conditions. The metallicity gradients observed in spiral galaxies mean that stellar giants in the outer regions of these systems formed with significantly lower heavy element abundances than their counterparts in the inner regions. Comparing the properties of stellar giants at different galactocentric distances helps astronomers understand how metallicity affects stellar evolution and mass loss processes. The upcoming generation of extremely large telescopes promises to revolutionize our understanding of stellar giants by allowing detailed spectroscopic studies of individual stars in nearby galaxies. These observations will provide crucial data for understanding how stellar evolution varies with metallicity and galactic environment, helping to constrain models of galactic chemical evolution and the formation of the first stars in the universe. The philosophical implications of stellar giants extend beyond their scientific importance to touch on fundamental questions about the nature of existence and change. These objects demonstrate that even the largest and most powerful structures in the universe are transient, subject to the same fundamental laws of physics that govern all matter and energy. Their brief but spectacular lives remind us that permanence is an illusion, and that beauty often emerges from the very processes of change and decay. The fact that we can study these distant giants at all speaks to the remarkable power of human curiosity and ingenuity. The photons reaching our telescopes from these stars began their journey when our ancestors were just learning to use tools, carrying information across vast gulfs of space and time to be decoded by minds that evolved on a small planet orbiting an ordinary star. In studying stellar giants, we participate in one of the most profound conversations possible, a dialogue between intelligence and cosmos that spans the entire observable universe. As we prepare to conclude our exploration of these magnificent cosmic titans, we find ourselves enriched by the journey we've undertaken together. We've travelled from the theoretical enormity of Stevenson 2-18 to the luminous power of W26, witnessed the dramatic evolution of WOH-G64, contemplated the revised measurements of UY Scuti, and marvelled at the complex beauty of VY Canis Majoris. Each star has revealed unique aspects of stellar physics while contributing to our broader understanding of how the universe creates and destroys its most extreme objects. These stellar giants serve as bridges between the familiar and the incomprehensible, objects large enough to capture our imagination, yet governed by the same physical laws that operate in our earthly laboratories. They remind us that science is not just about accumulating facts, but about developing new ways of seeing and understanding the universe around us. Through the study of stellar giants, we learn not only about stars, but about the fundamental nature of matter, energy, space, and time themselves. The uncertainties that surround our knowledge of these objects, rather than being limitations, represent opportunities for future discovery. Each unanswered question about stellar giant behavior points toward new observations to be made, new theories to be developed, and new insights to be gained. The dynamic nature of scientific understanding means that our picture of these cosmic titans will continue to evolve, becoming richer and more detailed with each passing year. The legacy of stellar giants extends beyond their immediate physical properties to encompass their profound role in the cosmic story of creation and destruction. These magnificent objects represent the universe's most dramatic examples of how matter can organize itself into structures that defy human comprehension. Yet they also demonstrate the fundamental impermanence that characterizes all cosmic phenomena. Their existence challenges us to expand our understanding of what's possible, while simultaneously humbling us with the recognition of how much we still don't know. As we've journeyed through these 5 cosmic titans, we've encountered measurement uncertainties that span hundreds of solar radii, theoretical contradictions that challenge our understanding of stellar physics, and observational phenomena that continue to surprise even the most experienced astronomers. These uncertainties aren't flaws in our scientific approach, but rather testament to the incredible complexity of the universe and the audacity of human attempts to comprehend objects that exist on scales almost beyond imagination. The rapid changes observed in stars like WOH-G64 remind us that the universe operates on timescales that can surprise us. While we often think of stellar evolution as occurring over millions or billions of years, these giants can undergo dramatic transformations in mere decades, forcing us to reconsider our assumptions about the pace of cosmic change. Such discoveries highlight the importance of continued observation and the value of long-term astronomical surveys that can track objects over extended periods. The role of these stellar giants in enriching the cosmos with heavy elements cannot be overstated. every atom of carbon, oxygen, and iron in your body was forged in the nuclear furnace of a massive star, possibly one similar to the giants we've explored tonight. When these stars reach the end of their evolutionary journey and explode as supernovae, they scatter these elements across vast regions of space, seeding future generations of stars and planetary systems with the raw materials necessary for complexity and life. This cosmic recycling process operates on scales that stretch human imagination. The iron expelled from a dying stellar giant today may not be incorporated into a new planetary system for billions of years, yet the process is inexorable, driven by the fundamental forces that govern stellar evolution and galactic dynamics. We are quite literally made of stellar remnants, temporary arrangements of cosmic material that have somehow achieved the remarkable ability to contemplate their own origins. The technological advances required to study these distant giants have pushed the boundaries of human engineering and ingenuity. The interferometric techniques that allow us to measure stellar radii, the sophisticated models that account for stellar pulsation and mass loss, and the space-based missions that provide precise distance measurements all represent triumphs of human creativity applied to the challenge of understanding the cosmos. Yet even our most advanced instruments struggle to capture the full complexity of these objects. The dusty environments that surround many stellar giants, the irregular variability that makes consistent measurements challenging, and the vast distances that separate us from these cosmic titans all conspire to keep many of their secrets hidden from view. Each observation represents a hard-won victory in humanity's ongoing quest to understand the universe. The international collaboration required for major astronomical projects studying stellar giants demonstrates how scientific curiosity can unite people across cultural and national boundaries. When astronomers from different continents coordinate their observations to study a single stellar giant, they participate in one of humanity's most noble endeavors, the collective pursuit of knowledge about our cosmic home. The educational impact of stellar giants extends far beyond professional astronomy to inspire wonder and curiosity in people of all ages. These objects provide tangible examples of abstract physical concepts, making ideas about nuclear fusion, stellar evolution, and the formation of elements accessible to anyone willing to look up at the night sky and wonder about the nature of the distant lights they see there. The ongoing debates about stellar size rankings remind us that science is not a collection of immutable facts, but a dynamic process of discovery and revision. As our instruments improve and our theoretical understanding deepens, we must remain open to revising our conclusions and embracing new paradigms. The humility required to acknowledge uncertainty and the courage to pursue truth, despite complexity, are essential virtues in the scientific endeavor. The future of stellar giant research promises discoveries that will continue to challenge our understanding and expand our sense of wonder. Next-generation telescopes and instruments will allow us to probe deeper into the physics of these extreme objects, potentially revealing new phenomena that we haven't yet imagined. The universe has consistently surprised us with its capacity for creating objects more extreme than we thought possible, and there's every reason to believe this trend will continue. As we stand on the threshold of new astronomical discoveries, we can anticipate that our understanding of stellar giants will continue to evolve in ways that surprise and delight us. Each new observation adds pieces to an ever-expanding puzzle, revealing the incredible diversity and beauty that exists in the cosmic realm, while simultaneously opening new questions for future generations to explore. The philosophical implications of studying stellar giants touch on fundamental questions about the nature of existence, impermanence, and our place in the cosmic order. These objects demonstrate that even the largest and most powerful structures in the universe are subject to change and eventual destruction. Yet they also show how beauty and complexity can emerge from the interplay of fundamental forces operating over vast scales of space and time. In contemplating these cosmic titans, we glimpse something profound about the relationship between size and significance. While these stars dwarf our sun and solar system by enormous factors, they also remind us that significance isn't simply a matter of scale. The processes that govern their behavior are the same fundamental laws of physics that operate in our earthly laboratories, connecting the largest structures in the universe to the smallest particles through the elegant mathematics of natural law. The story of stellar giants is ultimately a story about the universe's incredible creativity and the power of scientific inquiry to reveal hidden truths about the nature of reality. Through careful observation, mathematical modeling, and theoretical insight, we've learned to read the cosmic stories written in starlight, decoding messages that have traveled across vast distances of space and time to reach us here on our small blue planet. As you prepare to drift into sleep tonight, perhaps you'll carry with you a sense of wonder at the incredible diversity and scale of the cosmic realm. Among the gentle points of light visible in your night sky may lurk giants beyond imagination, stars so large they could swallow entire solar systems, so bright they outshine hundreds of thousands of normal stars, so complex they create their own weather systems spanning light years of space. These stellar giants remind us that we live in a universe of unimaginable beauty and complexity, where matter and energy organize themselves into structures that challenge our ability to comprehend their true nature. They serve as beacons of wonder in the cosmic darkness, inspiring us to continue our quest for understanding, while humbling us with the recognition of how much mystery still surrounds us. The measurements and observations we've discussed tonight represent humanity's best current understanding of these cosmic titans. But they also represent waypoints on a journey of discovery that will continue for generations to come. Each refinement in our measurements, each new theoretical insight, and each unexpected observation adds to the growing tapestry of human knowledge about the universe we inhabit. In studying stellar giants, we participate in a conversation that spans the entire history of astronomy, from ancient stargazers who wondered about the nature of the lights in the sky to modern researchers using the most sophisticated instruments ever created. We are part of an unbroken chain of human curiosity that stretches back to our earliest ancestors and will continue long after we're gone. The universe of stellar giants awaits further exploration, promising discoveries that will continue to surprise and inspire us. As our tools become more powerful and our understanding deepens, we can expect to uncover new types of stellar giants, observe previously unknown phenomena, and gain deeper insights into the fundamental processes that govern stellar evolution. These cosmic titans stand as monuments to the universe's capacity for creating objects of stunning scale and beauty, reminders that reality extends far beyond our everyday experience into realms where the familiar becomes extraordinary and the impossible becomes routine. They invite us to expand our sense of what's possible while maintaining the humility that comes from recognizing the vastness of what we still don't understand. The journey we've taken together tonight through the realm of stellar giants brings us to a profound realization about the nature of scientific discovery itself. We've witnessed how the universe delights in creating objects that push against the very boundaries of what we thought possible, forcing us to constantly expand our understanding of cosmic reality. As we close this exploration of the universe's most magnificent titans, consider this remarkable truth. The photons that carried the light from these distant giants to create the images we've shared tonight began their journey when civilizations rose and fell on Earth, when continents drifted across our planet's surface, when species evolved and went extinct. These ancient messengers of light have traveled across incomprehensible distances to reach us here, in this moment, carrying with them the stories of stars so vast they challenge our ability to truly comprehend their scale. The 5 stellar giants we've encountered represent more than just impressive statistics in astronomy textbooks. They are active participants in the ongoing story of cosmic evolution, the universe's way of transforming simple hydrogen and helium into the complex chemistry that makes worlds and life possible. Each of these stars is simultaneously creating and destroying, building heavy elements in their cores, while slowly tearing themselves apart through mass loss, preparing for the spectacular finale that will scatter their enriched material across the galaxy. What strikes me most profoundly about these cosmic titans is how they embody the universe's fundamental creativity. From the simplest possible ingredients, gravity and nuclear physics have collaborated to create objects of such staggering complexity and beauty that they defy our everyday understanding of what's possible. These stars exist in a realm where normal becomes extraordinary, where the familiar laws of physics are stretched to their absolute limits, creating cosmic laboratories where matter behaves in ways we can barely imagine. The uncertainties that surround our measurements of these giants aren't obstacles to understanding, but rather invitations to wonder. Each error bar in our calculations, each revision in our estimates, each unexpected observation reminds us that the universe still holds secrets waiting to be discovered. We are explorers at the edge of human knowledge, using light itself as our guide into territories where few have ventured before. As you settle into rest tonight, perhaps gazing up at the stars through your window, remember that you are witnessing one of the most remarkable phenomena in the universe, the emergence of consciousness from cosmic material. You are stardust that has learned to wonder about its origins, matter that has achieved the extraordinary ability to contemplate the very stars from which it came. The calcium in your bones was forged in stellar cores. The iron in your blood was scattered by supernova explosions. The oxygen you breathe was created in the nuclear furnaces of dying giants. This connection between you and the stellar giants we've explored tonight isn't metaphorical, but literal and profound. We are not separate from the cosmos, but part of its ongoing evolution, temporary arrangements of stellar material that have somehow achieved the remarkable feat of self-awareness. In studying these distant giants, we are the universe studying itself. Cosmic evolution reaching a level of complexity where it can contemplate its own magnificent creations. The future holds promise for discoveries that will dwarf even tonight's revelations. New telescopes will peer deeper into space, new techniques will resolve details we can barely imagine, and new theories will help us understand phenomena we haven't yet discovered. The stellar giants of tomorrow may make today's cosmic titans seem modest by comparison. The universe has consistently surprised us with its capacity for extremes, and there's every reason to believe that the most extraordinary objects are yet to be found. So as you drift towards sleep, carried by the gentle rhythm of your breathing, know that you rest within the embrace of a universe filled with wonders beyond imagination. The stellar giants we've encountered tonight continue their cosmic dance, pulsing and evolving, creating and destroying, participating in the grand symphony of existence that connects the smallest quantum particles to the largest galactic structures. Thank you for joining me on this journey to the edges of cosmic scale and human understanding. If this exploration of stellar giants has filled you with wonder about the universe we call home, I'd be grateful if you'd subscribe to join our community of cosmic explorers. Your support helps us continue these journeys to the frontiers of knowledge, connecting curious minds across the world in our shared quest to understand the magnificent cosmos we inhabit. Until we meet again among the stars, keep looking up, keep wondering, and remember that you are part of the most extraordinary story ever told. The universe awakening to itself through conscious beings who dare to ask how large, how bright, and how magnificent the cosmos can truly be. Good night and sweet dreams, fellow travelers in this infinite cosmic ocean. The stellar giants await our return. I wish you had an amazing time here with me. As always, I will see you tomorrow, right around this time. Until then, stay curious and keep wondering. This is Boring Science. Cheers.